In the previous video on the architectonic of simulation, I gave some basic definitions of what the architectonic of simulation is. I discussed some historical figures who contributed to theories of everything, and then I gave a general overview of what the model was, and then that was followed by a discussion of things that the architectonic of simulation has implications for going into the future. So here what I'm going to do is I'm going to make a short video series that discusses different taxonomic brackets of classes that are within the architectonic of simulation. And I'm going to begin this with the universal prototype, and then this video presentation will be followed by a video presentation on computation, and then ratiocination, and then instantiation. So in this video, there are 4 parts. In the first part, I'm going to give some definitions of the universal prototype, and then this will be followed in part 2 by fractals of the universal prototype. And then in part 3, I'll give some historical to contemporary expressions of the universal prototype. And then lastly, in part 4, I'm going to give some propositions about the universal prototype. Definitions of the universal prototype. The universal prototype consists of 2 words, universal and prototype. Well, the word universal, we know what the word universal means. It means that it applies across everything. Well, the word prototype derives from the Greek prototypon, which meant a first or a primitive form. We can subtract the word form and replace it with the word simulacra. And then that's the definition that I mean to convey here. A first or a primitive kind of simulacra. The issue with defining the universal prototype, and this is something I talked a little bit about in the previous video, is that you can't define or describe the prototype without doing so through its variations. And this is because it's universal. It's a universal prototype of simulacra. So the prototype exists at every conceivable building block of experience and every conceivable building block of simulation. And so the only way that we can really make sense of it or understand it is through our way of making sense of things and understanding things which are inherently populated by different kinds of prototypal variations that all share in common the same root prototypal structure. So it can get a little bit dicey in trying to explain it because every kind of explanation you give to it, you're applying it in the very act of describing it. The way that I explained it in the previous video was that domains orient into modes, modes iterate into tessellations, and tessellations propagate domains ad infinitum. So the word domain etymologically derives from the Latin domus, which meant house. And so what I'm really getting at here is that when it comes to domains, they're realms or fields or scopes or a set as an assembly of simulacra bounded by definable characteristics. And these definable characteristics are exhibited through the modes of the domain. The word mode etymologically derives from the Latin modus, which meant a way, manner, fashion, style, or a rhythm. And I thought that the word mode was a really good word to use for this because if you can recall from the previous video on the architectonic of simulation, when I talked about computation, that there was one domain, which is recursion, and then it has modes, which are static, dynamic, and multidynamic. Multidynamic being the combination of static and dynamic together at the same time. And the word mode allows us to have one word that represents all 3 of those things. It can be a fashion or a manner in terms of its statical state. It can also be like a way or a rhythm in terms of its dynamic state, and then it can have an overall style in terms of its multidynamic state. So the word mode allows us to sort of encompass all the different ways that a domain orients. Tessellation etymologically derives from the Latin tessellatus, which meant a minute arrangement of parts. So tessellations are mosaics, variegations, diversifications, strata, and plexification that come from the iteration of the modes. So the way that this all fits together in the universal prototype is that the universal prototype firstly is defined by having a bounded area of definable characteristics. And these definable characteristics are exhibited by the modes in which the domain orients. And then these modes, by what they are and how they act, create these tessellations of patterns. And then these patterns exhibit further characteristics, which are then the domains for the next iteration of prototype. So when we are talking about domains orienting into modes and modes iterating into tessellations, and then tessellations propagating more domains, what we're really talking about here is a fractal. And there are 3 fractal scales of the prototype. The first is the nested degrees of simulation. The second is architectonics of simulation of the nested degrees. And then third are orders of simulacra of the architectonic of simulations. And the thing is that the universal prototype occurs at every single one of these building blocks in this larger fractal scalarity. So the first is the prototype in nested degrees as architectonic simulations. The first degree is the universe simulation as the domain. It's the overall domain of the reality in which we all live. The second degree is simulators within the universe simulation as modes. And so when I say that the simulators within the larger universe simulation are modes, what I mean to say is that they're different orientations of architectonic simulations experiencing, internally representing the universe simulation as the overall domain. And then the third degree is simulators within the universe simulation as tessellation. So it's simulators within simulators within simulators. And a really basic example of this is that you can represent another person in your mind, and you can represent the way that they internally simulate reality. Similarly, we can do the same thing with computational machines, where we can create a computational machine simulated environment, and then we can create agents within that simulated environment that have their own internal simulations of their simulated environment. The prototype in architectonic simulations as orders of simulacra means that each of these degrees, they each have their own computation domain, ratiocination modes, and instantiations as tessellations within their own architectonic. So the universe has its own architectonic, simulators within the universe have their architectonic, and then simulators within the simulators have their own architectonic. And the whole point of the architectonic of simulation is to have a taxonomy of these universal classes of the simulation of experience that pervade across all these different kinds of simulations. But to stay on point, the last thing to be mentioned is the prototype in orders of simulacra. So within computation, there's the domain of recursion, and then it has its own modes of static, dynamic, and multidynamic, and then it has its own tessellations of object, subject, and transject. The ratiocinators are the modes of an architectonic, and their domains are the means of computation architecturally, processually, and then the architecture processes together as calculatory. And then each of these architectural, processual, and calculatory domains have their own modes, its own static, dynamic, and multidynamic expressions. And then they all share in common similar tessellations that are shared across all the ratiocinator modes. And then the instantiations are the tessellations of architectonics. And these domains can be any and all occurrences that derive directly from ratiocinators. And their modes can be any and all posture and means in which each of those individual, very much unique domains can occur. And then the tessellations are the patterns that are exhibited by those modes. So to summarize, there are three fractal scales of the prototype. There are orders of simulacra of the architectonic simulations that begin with instances of things that happen, and then they are prototypal with the ratiocinators in which they derive, which are prototypal to the computation in which the ratiocinators are expressions. And then all of the orders of simulacra as these tessellations from modes, from domains, belong to a larger scope of architectonics, of simulation. And then these exist in the layers of instantiations themselves, being tessellations making ratiocinators, which are modes of computation as a domain. And then these belong to even larger scope of nested degrees of simulation. So there are simulators within simulators from the third degree, which are nested within simulators at the second degree, and then the simulators at the second degree are nested within the first degree simulation of the universe. And the prototype recurs. It persists across all these different building blocks of simulation at every conceivable experience that we have and every conceivable kind of simulation that exists across to all of these things. Historical to contemporary expressions. So this is not a complete list. This is just a list of some of the folks that influenced me in my thinking in terms of describing what this universal prototype is. So in the negative 3rd century, there was Plato, and he had this notion of collection and division in Phaedrus. And then eventually Aristotle continued along with this and the notion of parts and wholes composing things, which was part of his metaphysic. And then in the 16th century, there was a Hermetic alchemist that went by the pen name of Hermes Trismegistus. And there's this quote that said, "As above, so below, as within, so without, as the universe, so the soul." And so you can see right away that there's a common thread here in the way that this proverb relates to the idea of the universal prototype. Because we're talking about something that exists at all scales of everything, from the most universal things to the most particular, and that it exists within ourselves and outside of ourselves, all across the universe. Well, in 1883, there was a guy by the name of George Cantor, and he came up with this idea of transfinite numbers. And the thing about transfinite numbers was that he discovered that you can have a series of numbers, but then you can have another series of numbers and another series of numbers, and then you can count those different series of numbers. And this kind of creates an interesting observation because it means that you can have an infinity of counting, and you can have another infinity of counting, and another infinity of counting infinitely. And so he tried to come up with a set theory to try to explain what was going on. Well, in the early 1900s, Ernst Zermelo and Bertrand Russell both came to this idea of a paradox. And the paradox is that if you try to say that there's a set that contains all sets, then that set containing all sets belongs to a larger set. And so every time that you say that a set contains all sets, you can reflect on it, and then you can have that belonging to a larger set. Well, in the meantime, in 1912, there was this guy, Stanisław Lęsiowski, who coined the term mereology. And his idea about mereology was to try to have a science about parts and wholes in their relationship with each other. A little while later, there's a guy by the name of David Hilbert. And what his thing was is that he wanted to have an axiomatic system for all mathematics. He and others were aware of this problem of transfinite numbers and sets containing sets, and he wanted to have an axiomatic system for all of mathematics that would be universal, that could apply across all sets containing all sets. And so he asked these questions that were epistemological questions at the foundations of mathematics that needed to get solved so that we could have certainty that our mathematical systems would be consistent. Well, in 1931, Kurt Gödel presented his incompleteness theorems, and his answer about whether or not you could have a universal axiomatic system for all mathematics was no. He showed that you can't have an axiomatic system that is complete and consistent at the same time, because an axiomatic system, he proposed, could not be used to prove itself. So, in order to avoid scaring away my audience by getting into mathematical explanations of this phenomena, I'll just give a basic example that I think everybody can relate to. So, if you have a belief about something, you can always ask the question, how do you know that your belief is true? When you ask that question, you have to include something new. You have to include a larger context or a larger scope in order to explain what you believe. And this is what Kurt Gödel did, is he showed that this is true in mathematics. So in 1932, Alonzo Church proposed something called lambda calculus. And in lambda calculus, he tried to come up with a mathematical system that could employ what Gödel had discovered. And so he proposed that there were types, and then there were operations, and then there were recursions. And these things occurred at every kind of computation that a person could perform. A little bit later, there was a guy by the name of Alfred Tarski, and he showed that through something he called the undefinability theorem, that this same idea didn't just apply to mathematics, but it could also apply to semantics in terms of what I had just used as an example with belief systems. He showed that the same phenomena happens with logic in general. So Alan Turing was one of Alonzo Church's students, and for his PhD dissertation, he wrote something called a system of logic based on ordinals. And he proposed that you can keep axioms that hold through recursions as part of the system. So developmental psychology was a very young science at the time, and he didn't really know anything about it, so he was missing any kind of notion about a universal process theory. But in the next slide, I'm going to talk a little bit more about that, because it turns out that increasing complexity eventually reaches a spot where you start to account for the entire scope of your experience, and everything becomes a variation of universal classes that you already understand. Well, a couple decades later, there was Koestler, and he had a notion of holons in his book Ghosts in the Machine. And holons is a sort of synonym to mereology. What holons are is they are units that are wholes and parts at the same time. And so in his book Ghosts in the Machine, he talks about that. And then in modern times, we have Ken Wilber's use of holon, which he describes through quadrants and levels. So the quadrants are perspectival, and the levels are building blocks of things. And so the perspectives divide between individual and collective versus internal and external, which gives you 4 different kinds of ways that people make sense of the world. And in each of these different ways that people make sense of the world, they're making sense of different dimensions of things, which he accounts for through these different levels of building blocks. So people take different approaches to trying to explain this kind of phenomena that we're talking about. People call it sets, or people call it mereology, or people call it holons, but they all share in common an attempt to explain what wholes and parts are and how they fit together into the larger building blocks of how things fit together. And people try to come up with understanding what the rules are for how it works. So I have 3 propositions about the universal prototype. The first proposition is that the universal prototype is supersymmetric, which means that it exists at every scale of simulacratic expression. The second proposition is that the universal prototype is acquiescent, and that means that it complies with any simulacratic expression. And then the third proposition is that the universal prototype is genetic, which means that it diversifies into variation of simulacra from sameness into difference. So we can combine these different propositions to say different things. So proposition 1 says that the universal prototype is supersymmetric, and proposition 2 says that the universal prototype is acquiescent. And so what this means is that the universal prototype exists at every scale in exactly the same way. And in exactly the same way, it allows for any possible simulacratic expression to occur, and it doesn't put up any boundaries on whether or not the expressions are capable of coming into existence or not. And I take this as an explanation for how people can conceive of all kinds of different things that don't necessarily previously exist in any human experience that people have had, which allows for people to invent entirely new things that nobody has thought of before. The proposition 1 that the universal prototype is supersymmetric and proposition 3 that the universal prototype is genetic can be combined to say that the universal prototype exists the same at every scale, but it also diversifies into variations. And the way that it does this is going to be similar across all of the different kinds of architectonics that exist. Architectonics of simulation can have different scopes, and this is something I'll talk a little bit more about in the video on instantiation. But this just means to say that when you have a universal prototype for a particular class of something, all the things that exhibit the characteristics of that class are going to be supersymmetrical to that class. And they can have variation of simulacra, but the variations of simulacra are going to follow along the genetic diversification of the classes along the architectonic of simulation taxonomy. So what this means is that we can use the universal prototype to understand how things become more diverse and have a super clear representation of it in our mind so that we can identify where things are supersymmetrical and where things diverge from that supersymmetry. Now, when we combine proposition 2 that the universal prototype is acquiescent and proposition 3 that the universal prototype is genetic, well, so there's definitely a overall spectrum from sameness to difference, starting with computation and then diversifying through ratiocinators and then diversifying further through instantiations. And the proposition 2 that the universal prototype is acquiescent, combined with this, means that it complies with any simulacratic expression. So the fact that people can imagine things that don't exist and then they can instantiate those things in the world, would be an example of what I mean by this. It puts constraints on the simulacratic experience, but the kind of constraints that it puts on the experience is in such a way where anything can be corresponded with anything else. And so when I say that the universal prototype is acquiescent and genetic, it means that there are innumerable possible expressions that will be different from other things that exist, but still maintain genetic inheritance of the architectonic of simulation. And the last thing to be discussed in this video is succeeding from undefinability. So there are things that persist through Gödel and Tarski's recursions, and Turing was onto this with his system of logic based on ordinals. So when you have a model that accounts for, describes, and puts into arrangement all simulacra across simulations, what you end up doing is you end up fitting together everything that you have experienced about everything. And you start to reach a point where everything becomes a variation of what you already understand. And we can take this in like a smaller scope to say that like you have experiences in everyday life, and then your experiences serve as the basis for new experiences that you have. And as you go through life and you experience new things, you include those things in your way of making sense of the world. And this is an ongoing process that you go through your entire life from birth to death. And so when we're talking about things that persist through the recursions, and we're talking about the architectonic of simulation, we're talking about constructing a model in our minds that is as supersymmetrical as possible to things that persist across all human experience in all simulations. And so every system that is internally complete but externally inconsistent, and internally consistent but externally incomplete, shares in common prototypal, supersymmetrical, acquiescent, and genetic traits. So if you think about tessellations as being sort of like theorems that are different expressions of rules that are followed by the different modes of a domain, and then you have to explain that domain by zooming out. Well, now you're zooming out, and that domain becomes a domain in a larger tessellative set that then follows higher order types and operations as static and dynamic, which are composed together into a larger multidynamic state, which then becomes the larger domain. And so the universal prototype is exhibited at every single one of these Gödel iterations. And then it turns out that you go from instantiated occurrences into ratiocinators, and then you go from ratiocinators into computation, and then from computation you go into the prototype. And the prototype shows us, as I stated earlier in the video, that there's actually like even larger scopes of fractal expressions of the prototype, going from the domains, modes, and tessellations within orders to the architectonic as a whole, where computation is the domain, ratiocinators are the modes, and instantiation is the tessellations, to even the larger scale of the 3 degrees of nested simulation, where you have simulators within simulators, and then you have simulators within the universe, and then the universe itself. And so if you take like Gödel's incompleteness and completeness theorems to say that everything is relative, well, if you're making a statement that everything is relative to a larger whole, but you have a way of organizing the trajectory of the development of integration of all the ideas that you have in the larger scope, eventually you reach a point of apex where everything converges. And this is the etymological singularity that I mentioned in the previous video on the architectonic of simulation. And it also, I think, lends to the idea of the technological simulation, where we can implement everything that we understand about everything across our species and all of our experiences into a unified, coherent model that can iterate over time as we learn new things as a species. So it turns out that Gödel wasn't necessarily wrong about what his theorems were. It's just that they belong to a larger scope of increasing complexity of understanding how the world works. And so the processes of iterating into increasing complexity of understanding everything proceeds along, first of all, recursions of computation, and then second of all, through ratiocinator trajectories, and then third, through instantiations. And all of this can be well defined, and that's what the architectonic of simulation is for. It's for us to include all the developments of all the conceptions of all of our experiences that we have and fit it all together into the larger scope of the human experience. So what I'll be talking about in the future videos on computation and ratiocination and instantiation is I'll be talking about the same idea in the context of those brackets of the taxonomic spectrum of the architectonic of simulation. So thanks for watching. If there's anything that you have to add, whether it's for or against the model, or just some associations that you think are good to make to the kinds of things that I was talking about, you can go ahead and leave comments in the section below. I'll be making more videos in this series about once a week. The next video, like I said, will be on computation, and then that will be followed by a video on ratiocination, and then I'll make a following video on instantiation. After I make those videos and I've given a description about all the different aspects of the model, then I can start making videos that apply the architectonic of simulation across a wide array of different topics. So I look forward to doing that, and I look forward to hearing any comments anybody has to say. And with that, thanks for watching again, and have a great day.